Bismillahirrahmanirrahim. Assalamu alaikum. In our today's video, we will discuss about the lag compensation. Ideal integral compensation with its pole on origin requires an active integrator. If we use the passive network, the pole and zero are moved to the left, close to origin, as shown this figure C. One may guess that this placement of the pole, although it does not increase the system type, does yield an improvement in the static error constant over an uncompensated system. Without loss of generality, we demonstrate that this improvement is indeed realized for a type 1 system. So here we can see that this is type 1 uncompensated system. In this figure, this is type 1 compensated system, and these are the compensator pole 0 plot. So the static error constant for the uncompensated system is this, and for the compensated system, the static error constant will be this one. So which static error constant will be higher? The compensated one. So as the compensated static error constant is higher, so the steady state error will be reduced in the compensated system. Here we can see that the effect on the root locus of adding the lag compensator. The uncompensated system's root locus is shown in the A figure, where point P, this point, is assumed to be the dominant pole. If the lag compensator pole and zero are close together, the angular contribution of the compensator to point P is approximately 0 degree. Thus, in the next B figure, where the compensator has been added, the point P is still approximately the same location on the compensated root locus. What will be the effect on the required gain K? After inserting the compensator, find that K is virtually the same for uncompensated and compensated system. Since the length of vector drawn from the lag compensator are approximately equal and all other vectors have not been changed appreciably. So for improving the transient response, the objective is to design a response that has a desirable percentage overshoot and shorter settling time. For a faster transient response than the uncompensated system, we will try to achieve the objective using the cascaded compensation. So far, we discussed only how to reduce the steady state error without affecting the transient response. Now we will discuss two ways to improve the transient response of feedback control system by using the cascade compensation. Typically, the objective is to design a response that has a desirable percentage overshoot and shorter settling time than the uncompensated system. These two techniques are ideal derivative compensation and the lead compensator. The first technique that we will discuss will be the ideal derivative compensation. With ideal derivative compensation, a pure differentiator is added to the forward path of the feedback control system. We will see that the result of adding differentiation is the addition of 0 to the forward path transfer function. This type of compensation requires an active network for its realization. Further, the differentiation is a noisy process. Although the level of noise is low, the frequency of the noise is high compared to the signal. Thus, differentiating high-frequency noise yields a large unwanted signal. The second technique does not use pure differentiation. Instead, it approximates differentiation with a passive network by adding a zero and a more distant pole to the forward path transfer function. The zero approximates pure differentiation as described previously. In our next video, we will discuss these two techniques, ideal derivative compensation and lead compensator, in detail. Thank you.